Imagine for a moment Earth's ancient past, but not just, as an idea. Imagine it as something tangible, something preserved in this, well, incredible time capsule. We're talking about a block of ice 50,000 years old, pulled from deep within the West Antarctic ice sheet. And this isn't just frozen water, Anna. It's like a frozen archive of the atmosphere itself, full of these tiny, tiny bubbles of ancient air. And what these bubbles are telling us, well, it's pretty profound, actually, about our past and definitely about our present. So today, our deep dive is digging into this really fascinating new study. It's just been published in PNAS Proceedings of the National Academy of Sciences. Pretty prestigious. Scientists from Oregon State University, Kathleen Went and Christo Buzzard, were the leads. They meticulously analyzed these little air bubbles. And their findings, they give us this really sobering look at our current climate situation because they reveal that the speed of carbon dioxide rise today, it just completely dwarfs anything nature did on its own, at least for the last 50,000 years, even the fastest natural spikes. So our mission here is to unpack what this ancient ice tells us about Earth's own carbon cycles, right? To understand the mechanics behind those natural CO2 burps they talk about, and then crucially compare that history to the rate of CO2 increase we're causing right now.
That's exactly right. It's not just history for history's sake. It's about understanding the planetary machinery,
Yeah.
to really grasp how unusual, how unprecedented our current moment is. What does this journey way back into the past actually show us about the picture for our future? Which is frankly a bit chilling.
Okay, so how do they even do that? How do scientists read the past climate from a chunk of ice? It sounds kind of like science fiction.
Yeah, it is pretty amazing, isn't it?
Yeah.
Well, they drill down, way down, into these huge ice sheets like the West Antarctic Ice Sheet Divide. They call it the Wars Divide. For this study, they went about 2 miles deep, 2 miles. And the ice they pull up, these long cores, they'd have layers, like tree rings.
Yeah.
And trapped in those layers are the tiny air bubbles, actual samples of the atmosphere from, 10, 20, 50,000 years ago.
Wow. So each bubble is like a tiny snapshot of the air back then.
Exactly. It preserves the mix of gases, including CO2 that was in the air when that snow fell and eventually compacted into ice. Then comes the lab work. Really detailed chemical analysis on these tiny bubbles to figure out precisely what was in that ancient air. It's incredibly painstaking work.
Okay, so we often hear this argument, right? That Earth's climate has always changed, CO2 has gone up and down naturally, and, well, that's true.
It is true, absolutely. The planet has natural cycles.
But what makes the study stand out, you were saying, is looking at the speed of those natural changes, the fastest ones.
Precisely. They wanted to find the absolute peak rate of natural CO2 increase over this whole 15,000-year period.
Yeah.
And they found these rapid increases were linked to something called Heinrich events, which happened during past glacial periods, so ice ages.
Heinrich events, okay. Sounds significant. What exactly were they? Break that down a bit.
Yeah, they were pretty dramatic climate shifts. They're named after a German marine geologist, Hartmut Heinrich. Essentially, you had these massive armadas of icebergs breaking off the big Laurentide ice sheet over North America. Huge chunks. This dumped enormous amounts of fresh water into the North Atlantic. And that didn't just cool things locally. It set off this whole chain reaction globally, affecting climate patterns far, far away.
A chain reaction. Okay. So it wasn't just colder in the North Atlantic. What else happened?
Well, it messed with ocean circulation. It impacted things like tropical monsoons. And crucially for this study, it affected the big westerly winds in the southern hemisphere. These events are like natural experiments, They show us how quickly the carbon cycle can shift on its own. So looking at the numbers they found, the biggest natural jump was about 14 parts per million, 14 ppm of CO2. And that rise took roughly 55 years. This was during one specific event, Heinrich Stadial 4, or HS4.
14 ppm in 55 years.
Okay. Still sounds kind of fast for a natural process. It was fast. For nature, that was the fastest they found. There were other jumps, too, maybe happening every 7,000 years or so. Sometimes smaller, like 12 ppm over 75 years during HS1. Or even quicker, smaller, like 7 ppm in just 15 years during HS2. But that 14 ppm in 55 years, that was the record holder, the fastest natural rate in 50,000 years.
Right. And what's the theory? Why did the CO2 jump like that during these events? Where did it come from?
Well, the evidence points pretty strongly towards the ocean, the deep ocean. They found a few key clues lining up. First, these CO2 jumps happened at the same time as sharp but short-lived increases in methane, another greenhouse gas. And second, the CO2 itself had a specific chemical fingerprint, what scientists call its isotopic composition, the 13C-CO2. It was depleted, meaning it was lighter carbon. And that signature, it points directly to carbon that's been stored in the deep ocean for a long time, not, say, from volcanoes.
Okay, so the fingerprint says ocean. What made the ocean suddenly release all that CO2?
The trigger seems to be those southern hemisphere westerly winds we mentioned. The evidence suggests that during these Heinrich events, the winds got stronger and shifted towards the South Pole. And when those winds intensify and move poleward, they churn up the Southern Ocean more vigorously. It's a process called Southern Ocean ventilation. Imagine stirring a fizzy drink. The gas comes out faster. These stronger shifted winds brought deep, carbon-rich water up to the surface, where that stored CO2 could then escape into the atmosphere, like, as the study puts it, these large burps of CO2 coming out of the oceans.
Large burps. Okay, vivid image.
Yeah.
Is there other evidence supporting this wind-ocean connection?
Yes, there is. They also saw Antarctic temperatures rise slightly during these events, about 0.6 degrees Celsius on average at the ice core site. And even the temperature of where the moisture originally came from, the vapor source, went up about 0.4 degrees Celsius. It all fits together. The winds shift, the ocean churns, CO2 comes out, temperatures respond. It's a consistent picture.
Right. Now, this is where it gets, well, really stark. Connecting that past to today, the lead author, Kathleen Went, she said, the rate of CO2 change today really is unprecedented. How unprecedented are we talking?
We're talking profoundly unprecedented. It's actually staggering when you compare the numbers directly. Remember that fastest natural rise, the 14 ppm of CO2 that took nature about 55 years to achieve during that big Heinrich event?
Yeah, 55 years for 14 ppm.
Okay, so today,
Yeah.
we're pumping out so much CO2 from burning fossil fuels that we're seeing that same 14 ppm increase happen in just 5 or 6 years.
Wait, say that again. 55 years naturally versus 5 or 6 years now?
And that's right, 5 or 6.
Wow,
No, I mean,
that's almost unbelievable. So the rate today is literally 10 times faster.
10 times faster, at least. Our current human-driven rate of CO2 increase is 10 times higher than the absolute fastest natural rate these scientists could find evidence for in the last 50,000 years. It puts into perspective what we're doing. We're outpacing even the most abrupt natural shifts known in recent geological time by a huge margin.
Okay, that really lands the point. So what does this mean looking forward? You mentioned those westerly winds again.
Right. This is where it connects to future projections. Climate models generally predict that as the planet continues to warm, those southern hemisphere westerly winds are likely to get even stronger.
Uh-oh. And based on what we just learned about the Heinrich events, stronger winds mean?
Potentially less help from the ocean. Remember how stronger winds help release CO2 from the ocean in the past? Well, today, the Southern Ocean is actually doing us a huge favor. It absorbs a significant chunk of the CO2 we emit, acting as a carbon sink. But if those winds strengthen significantly due to warming, the worry is it could make the surface waters more turbulent, less stable, and that could weaken the Southern Ocean's ability to absorb CO2 from the atmosphere.
So the ocean that's currently helping buffer climate change might become less effective at doing its job precisely because of the warming we're causing. That sounds like a dangerous feedback loop.
Exactly. It's a potential positive feedback. Warming leads to stronger winds. Stronger winds potentially weaken the ocean carbon sink, meaning more CO2 stays in the atmosphere, leading to more warming. You see the cycle. Kathleen Went highlighted this specific concern. She said, we rely on the Southern Ocean to take up part of the carbon dioxide we emit, but rapidly increasing southerly winds weaken its ability to do so. Just underscores how interconnected everything is and how pushing one part of the system so hard and so fast can have these cascading and potentially self-reinforcing consequences.
This has been, well, incredibly insightful. This deep dive really drives home that point. Yes, Earth has natural climate cycles, we know that. But the speed and the sheer scale of what humans are doing now with CO2 emissions, it's just in a completely different league. It dwarfs those fastest natural events from the last 50,000 years. We've literally peered into ancient air bubbles to see how Earth's climate machinery works, how linked the oceans, the winds, the CO2 are. Which leaves us with a pretty powerful thought, doesn't it? If natural processes, just by shifting winds and ocean currents, could cause these significant CO2 burps, and now humanity is driving change 10 times faster, what does that really imply for our future? How much can we keep relying on these natural systems like the Southern Ocean to absorb our impact? And maybe more importantly, what kind of responsibility does this knowledge put on us right now? What really stands out to you after hearing all this?